Hello and welcome to another video. In this video we're going to be going over find first and last position of an element in a sorted array. And in this problem you're given an array of integers sorted in non-decreasing order. Find the starting and ending position of a given target value. If the target is not found, return -1, -1. Then you must write a log n runtime complexity function. So obviously you could just like do if you didn't want to do log n, you could just go through manually, right, and just check for the numbers. That would be super easy. That would be like an easy problem. And that would be an end time. But let's kind of go through the solution here. So we're looking for 8. So the first index of 8 is at index 3, and the last index is at index 4. And then for 6, it's not in the array, so we return -1, -1. And then for 0, it's not in the array, so we return -1, -1 again. So essentially, let's kind of walk through this. Let's say we're looking for something like 8, and we have some sorted numbers like 1, 2, 3, 4, 4, 8. Let's just say we have a bunch of 8s. Something like this. So the way to do this, obviously, if they tell you to write a log n function, there's pretty much like only one, right? Binary search. And your array is already sorted, which is like a big hint for binary search. So how would this work in a binary search? Like, you could find an element, you could find an 8 pretty easily, but how would you know if it's the leftmost 8 or the rightmost 8, right? So we're actually going to break it down into two parts. We're going to find the leftmost 8, and then we are going to find the rightmost 8. So for the leftmost 8, that one's pretty straightforward. We'll kind of walk through it. Essentially, you make a left and a right pointer, and you look for an 8, and you have some like result. You can set it equal to -1. So we'll set our result equal to -1, and we look for an 8. And if we find an 8, we're going to set our result equal. So I guess there's like three things that can happen, right? So for the leftmost. So there's 3 things that can happen. So let's write that down. So A, like, what are the 3 things? Okay, so number is greater than 8. So if we have a number that's greater than 8, then we're to the right, so we need to go left, right? So here we go left. 2, number equals 8. What do we have to do here? Well, we probably want to record that. So we want to like record that. And then go left and see if there's anything else to the left. Right? So like if we hit this 8, we are going to record this index, but then we want to check like is there anything more to the left? And then finally, if the number is less than 8, then we go right. And these are our conditions for finding leftmost 8. So let's kind of use this and see if we get a solution. Let's just have a bunch of 8s. Like, hopefully we don't get the answer right away, but let's kind of see. So let's just see what this index would be. So this is like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the middle index would be, what, like 5 or something? So like here, I think. So we would actually find it right away. And ideally that doesn't happen. So let's maybe add like a 5. And do it again. Okay, so now we have 10, so we would go here, I believe. Another 5, yeah, well, let's just say, I'm not exactly sure where the pivot, I think it's here, but whatever. So let's say our left and right's here, our pivot value would be here, and we are gonna kind of check like which one of these cases this is. So this is gonna be less than 8, right? So if we're less than 8, then we need to get rid of this subsection, and we need to go to the right. Right. So to go to the right, we're just going to make left equal to this part here, and we're going to get rid of all this. Now we're going to get a new pivot value. It's going to be in the middle. And now we actually found an 8. So we do want to record this index. So what is this index? This is 1, 2, 3, 4, 5, 6, 7, 8. So we're going to update this index to be 8. And then we're going to figure out, like, so we did find an 8, but we need to see if there's any more 8s to the left. Like, if we found this 8, if there's 8s to the right, we don't really care, right? We're trying to find the leftmost 8. So we're going to set our right equal to this 8. And actually, there we go. Get rid of all that. So our left and right's here. So now our new pivot value will be here. And we have found an 8 again, and this 8 is obviously... So we're always going to get rid of, like, if we found an 8, we're always going to get rid of the stuff to the right. And I was actually doing this before that, and I realized it's like unnecessary. I was trying to like minimize or maximize our result. But the thing is, if we find an 8 and then we're like getting rid of that, our new search area is always going to be to the left of that. So every new result we find is going to be better than the last one guaranteed. So we don't need to like min-max it. We can just say like if we get a new result, let's just use that instead. So we have 1, 2, 3, 4, 5, 6 here. So we're going to update this to index 6. And then we're going to try to find something to the left of that. So we're going to make right over here, get rid of all that. And now there's nothing left, right? And so that is the leftmost state. So if you see this is 0, 1, 2, 3, 4, 5, 6. So the leftmost state is at index 6. And we have like our logic for it, pretty straightforward, right? So let's actually get rid of, let's try to like reuse this ideally. And we can add the 5 again. Okay, so our leftmost state is at index 6. We're going to write that down. And we're going to try to figure out what we need to do for the rightmost state. We're going to have another variable. Let's set it equal to -1. And if we don't find the number, then we're never going to update this, so we can just return -1. So let's kind of like take what we have for the leftmost state. Can I copy it? I think so. And let's add it over here, because it's going to be very similar. Okay. So for the rightmost state, if the number is greater than 8, we still want to go left, right? Like if we're trying to find the rightmost state, if we're too far, we're still going to want to go left. But this is the one that changes. If we find an 8, like let's say we find this 8 here, we don't really want to be I don't know why it's telling me this, but whatever. We don't really want to be going left now. We want to be going right? So if we find some solution, we want to be going right. And so that's what we're going to do. So we're going to go right. So if we find an 8, we're going to go right instead of left. So let's write that down. Okay. Record that and then go right this time. And see if there's anything to the right. So we find an 8. We're trying to find the rightmost. Now we go right instead. And if we are less than 8, then we still do the same thing. So the only difference really is once you get to the number, if you're trying to find the leftmost one, you would go left after you find something, and when you're trying to find the rightmost one, you would go right. So let's walk through this again for our stuff. So let's just say our pivot's here. Not 100% sure, but let's just say it is. So here we are less than 8, so we're going to go right, just like before. So our left is going to be over here. We are going to get rid of all of this. And now our new pivot is going to be over here. So we did find an 8, and this is 1, 2, 3, 4, 5, 6, 7, 8, just like last time. Right, so we're going to update our result from -1 to 8. And now we're trying to find the rightmost element. So instead of getting rid of this section, we're going to get rid of the left section. So we're going to update the left to be over here. And now we're going to have a pivot over here. This is 8 again. So this is 9, I believe. Yeah. So then we're going to update our result to be 9. And we're going to try to go right again. So our left is going to be over here, our right's going to be over here. This is too big. So then if it's too big, we're going to update our right to be over here. And now our left is bigger than our right, so we have an invalid binary search, so we don't have anything else to search for. So our leftmost is 6, and our rightmost is 9, which is correct, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. That's pretty much all you need to do is just a double binary search. And I'm going to try to make a helper function here because we're literally copy-pasting the same code with this one difference here, this B difference. Everything else is literally going to be all the same. So we're just going to make a helper function called like binary search or something, and then just pass in like, are we checking the left and checking the right? Set the result equal to -1 for both of them. And then if we never find anything, then in fact, we can even return early. If that's like a slide optimization, we can say like, if we try to find it the first time and we find nothing, then we could return -1, -1. So that's like a slide optimization. It's not going to affect runtime, but instead of running 2 times log n time, it'll run like log n time or something. And yeah, so let's code that up. So let's make a helper function called binary search. So we can call it like def search. And what do we want to take in this function? So all we really need is if we're checking to the left and we're checking to the right, right? So we can, instead of left or right, we call it like first or last. So we can call this like first or something, right? So let's do that. So we're going to make our result equals -1. We are going to have a left and a right, and they're going to be 0 and like nums -1, all the same. And then we're going to have the while left is less than or equal to right. We're going to have our 3 conditions, right? So we're going to get the pivot, call that P, equals left plus right. Just typical binary search template. On 2. So now we're going to check if the value is equal to, if the value is equal to the target. So if P equals target, then we're going to update our result, right? So result equals P. And so here we have to check which way to go, right? So if first is true, if we're trying to find the first element, then we want to go left. So that's going to be right equals P minus 1. Otherwise, if we're trying to get the rightmost element, then we're going to go right. So then we'll say left. This should not be left. This should be R. This should be RML. Lazy LeetCode coding, 1-letter variable is pretty good. Okay, left equals P plus 1. So that's going to be the case. That's going to be the only difference. So if we're trying to get the leftmost one, we're going to go left. If we're trying to get the rightmost one, we're going to go right for that helper function. Now we are going to have an else case. So else nums P is less than target. Then we are going to want to go right in both cases. So that's going to be left equals pivot plus 1. Else, if we're greater, we want to go left. So that's going to be right equals pivot minus 1. Now we simply return, after we're done, return result. So we can get those values. So we can say like first equals search true. And then we can say if first is -1, then we just return -1, -1. So if first equals -1, return -1, -1. We don't have to look for the other one if we didn't find the first one, or if we can find the second one. Then we're going to have the second one, or the last, or whatever we want to call it, equals search false. And now we can just return those two. So return an array of first, last. So we're just calling this function twice with basically the same thing, except for this one change here. Let's see what happens here. Looks like we have something that worked. Yeah. And you can see this one's pretty efficient. I do think most people are going to have the same code. So if you do have the early termination, it's probably going to be a little bit faster on LeetCode. I guess we can test for that. Kind of curious. But complexity-wise, it'll be the same. Yeah, so that preemptive return is a little bit faster for actual test cases, but for a big O, it doesn't matter. Okay, and then for the time here, so this is going to be a log. Obviously, they tell you must write a log n function. So it's log n. We're just doing 2 searches. Each one is log n, or we're doing 1 if the first one failed. But worst case, it's 2 times log n, which is log n. And space. So in this function, as usual, in a normal binary search, in most of them, they're O of 1 because you just have like a result variable and a left and a right. We're not making anything extra here. So O of 1. And yeah, kind of a not too bad of a problem, pretty simple. And if you did like this video, please like it and please subscribe to the channel, and I'll see you in the next one. Thanks for watching.